when you multiply things, matrices and vectors, the number of columns here has to match the number of rows here. And what we expect to get is this goes away, and we'll get a 2 by 1 object. And the 2 by 1 object we get is, we'll call this A, B, C, D, and we can call this X, Y. So if I write X like this, I could put X1, X2, or I could write X, Y. This would be bold. This would not be bold. You prefer me to write X1, X2, or X, Y? Doesn't matter. You'll see both. Okay. What you've got to do is you've got to take the row times the column. So the first term here would be A, X1 plus, this here actually is addition. This would be AX1 plus BY, sorry, AXBY. So it's that times that, that times that. And you add them together. That would give you the first element. And then the second row here would be C times X plus D times Y. So the first row times the first column, element by element, add them together, gives you the first element here. And the second row times the first column gives you the second element over here. So this is a 2 by 1 object, because this is a number and that's a number. So that's two numbers. Everybody see that? If I were to take two matrices, A and B, and I would multiply those together, I'd write A times B. A times B, let's say A, B, C, D, alpha, beta, gamma, delta. Let me do a multiplication here. Now, because this is 2 by 2 times 2 by 2, and this goes away, those have to match up, and they go away. I'm left with something that I expect to have 2 by 2 elements. So two matrices, 2 by 2, 2 by 2, give me another 2 by 2 matrix. To get the first element here, I have to take the first row by the first column, multiply those element-wise, add them up together. So I get alpha A plus beta D. So, sorry, alpha A plus gamma B is the first one. And the second one would be A times beta, B times delta. Does everybody see how I did that? And the third one, I've got to take this row times the first column, this row times the second column. So to get, this is the second row, first column. Second row, first column. Second row is alpha C plus gamma D. Yeah. So and this is delta, this is D. And then second row, second column, second row, second column, second row, second column, beta C plus delta D. Okay. Now we're going to see something really interesting. Who believes we can see something interesting now? So on a scale from 1 to 10, how boring has this been so far? Come on, how boring? Like, huh? 10 being really amusing, 1 being horribly boring. 2, okay, yeah, that's about what I give it. So what I'm about to tell you is probably an 8. A times B is not equal in general to B times A. Is that amazing? If it weren't for this, life wouldn't exist. There wouldn't be any quantum physics. Matter wouldn't be able to interact. Okay, so let's see why. So I'm going to write alpha, beta, gamma, delta times A, B, C, D. And in order to get the first term over here, that would be A times alpha plus beta times C. And if we have a look here, we have A times alpha, yes, that's the same. But here we have gamma B, and here we have beta C. So it's not the same. So there's only certain cases where just because of the special structures, it turns out to be the same. But in general, it's not the same. So all the stuff that we learned about arithmetic that seems so natural, which is, this is called the, what property is it called again? It's not the commutative, I think it's the commutative property of arithmetic. In arithmetic, AB is equal to BA with scalars. But in matrices, AB is not equal to BA. And it's very important the order in which you multiply matrices. Okay. Now, we can come to a simple example which is in the book, and that is projecting future loggerhead total abundances. Now in this model, this model takes a very simple approach, and it says, let x and y, I'll make this a little bigger. So x and y are the current abundances of juveniles and adult loggerheads. And we're making the assumption that approximately 50% of juveniles survive to the next year and do not mature. And approximately 0.1% of juveniles survive to become adults. And adults on average produce 80 immature loggerheads each year. And 80% of adults survive to the next year. Now we'll become more familiar with how to write down such equations. But this equation says that the abundance of juveniles next year is equal to half of those that are around this year, plus 80 times the number of adults. So that's a big number. But it also says that the abundance of adults next year, if we look at all the juveniles, only 0.1% of them become adults, but 80% of the adults remain adults. So I don't know if these numbers are any good, but we know with turtles that a female might lay 80 eggs, but when these eggs hatch, they hatch on the beach, and these little turtles have to rush across to the beach, into the water. And they get picked off by, well, firstly, how many of those eggs will hatch? They'll get picked off by birds. When they get into the water, there'll be things waiting to eat them. So the chances of finally becoming an adult, which may be 5 years later, I don't know how long they take to mature, Only 1 in 1,000 will make it. So in matrix notation, if we write down x at t plus 1 is 0.5 x at t plus 80 y of t, and y of t plus 1 is equal to 0.001 x at t plus 0.8 y of t. So last time we talked about how to write these, we talked about a very simple model. If I could just maybe go back and open up that file from last week. We wrote down this model, and we showed how you can write it as a matrix model. In this case, we've got 4 numbers, not 3. This one's a 0 in this particular model. You can then write this model out in this way. In order to calculate what's going on next year, you take these numbers and you multiply by the x's. So for example, if x is 10,000 and y is 50, then you take 10,000 and 50 and you multiply it by this matrix, and then next year you get 9,050. And if you do this again, you take 9,000 now and 50, and you multiply it by this matrix, then the following year you'll have 8,500. I don't know if the time, I think the time span here is a year, so let's say it's a year. And so you can keep going along, and what you'll find is that this looks like bad news, because it looks like these turtles are reducing on the order of something like close to 10% a year. So quite soon there'll be none left. Now, one of the things about these equations is that if you remember in I don't know, 8th grade, maybe you would do linear equations where you'd have an equation that looked like, something like 3x plus 4y equals minus 6, 2x minus 7y equals 4, and you're asked to solve that. Remember doing those things. Did you use matrices then? Okay. So matrices now make this process. If you know how to work with matrices, then there are very standard ways to solve this and to understand how these work and when you get solutions and when you don't. Now you might say, this is simple, I know how to do this. But if I gave you a problem where I said 13x1 plus 6x2 and 17x 10,000 is equal to a1, and then I went all the way down and I gave you another equation and I had a 10,000, then you're not going to try and calculate that by hand. Basically, you've got 10,000 unknowns, and you've got 10,000 equations and 10,000 unknowns. You need to solve them. Do people solve equations like this today? They do. Not by hand. So it turns out that in a lot of complex models, like predicting the weather, you set up a big grid that represents a grid that covers the whole atmosphere of the Earth. And every mile or every kilometer, you have a point on the Earth's surface, and then you go up 20 kilometers or 30 kilometers. And you characterize the wind speed, the humidity, and the temperature at each of these points. And then you want to predict what's going to happen, and you want to predict where the wind's going to go, where water's going to accumulate, and so on. Now, these equations are equations of physics, and they're nonlinear. But if you linearize, remember we talked about linearizing a model? So you've got these nonlinear things. Now, if you linearize this model and you take a small interval of time, like 10 minutes, you can get a linear approximation to the nonlinear process. And you keep iterating over these millions of points every 10 minutes, or every 1 minute, depending on how fine a resolution you have and what kind of data you have for your model. So you get vast systems of equations that, once you linearize them, are equations like this that involve millions of variables. And this is what we use on supercomputers to calculate how the weather is going to progress. And why we get it wrong is because, firstly, we're approximating by measuring the state of the atmosphere every 1 kilometer, say, or every 100 meters, or every 10 kilometers. I mean, we used to do it when computers were small, every 100 kilometers, but now we have much finer resolutions. And then we also have to be able to measure what's going on at all these points in order to calculate what will happen at the next point. So we have to have a set of initial values that help us calculate. And as you integrate this over time, errors will creep in. But in order to integrate this over time, you sometimes have to solve these huge systems. Fortunately, we don't have to be too interested in that. But we do have to be interested in it for much smaller systems where we have on the order of 10 or 20 dimensional processes. Because these are things that we use to model populations. Like, if I said to you, we want to model whether leopards, or let's say Siberian tigers, are going to go extinct, we would have a number of tigers, and we would age them by years, and we'd have a look at the number of newborns, the number of 1-year-olds, 2-year-olds, up to age 10 or 15. And so we would build a model to see what's going on with that. And we'll talk about some of the models like this. But when it comes to solving a matrix equation like this, and we can write down more generally A, B, C, D, X, Y, X, Y. And then I can take this out and write this as X, Y. So this would be AX plus BY equals E, CX plus DY equals F. So that would represent that matrix equation. So if we took that and we multiplied it out, we would get this. And if we multiply this out, we get the equations. Provided B is not equal to 0, we can divide through by B. And then that's for the first equation. And then we can substitute where we have Y. We can put this. So we can say CX. And we can replace Y with this thing over here to get this equation. And then we can solve for this. We can go through the process of rearranging terms. And we would get something that looked like that. And then provided B, which we assumed not to be equal to 0, we can do that. Then we can multiply through the top and bottom by B. And we can get BC minus AD times X is equal to this. And once we solve for that, then we can substitute in any one of the equations, and we can get the value for Y. So solutions are given to the above formula, provided that B is not equal to 0, and BC is not equal to AD. That's BC. Now, BC is not equal to AD. Now, if we look at this matrix, A, B, C, D, we have something called the determinant of the matrix. And the determinant of the matrix, sometimes written as DET of the matrix, is equal to this times that minus this times that. So it's equal to AD minus BC. So the determinant is equal to AD minus CB, or BC. It doesn't matter, because these are scalar values, so you can write them any way around. If this is not equal to 0, then this condition holds. And if this is equal to 0, if the determinant is equal to 0, then we have a problem. So when we try to solve a matrix, when we try to solve an equation, we have to check that the determinant is not equal to 0. So let's have a look at this matrix A over there. Is its determinant equal to 0? What do you think? Matrix A, what is its determinant? It's 1 times 4 minus 2 times 2. That's equal to 0. So if we try to solve this, we should expect a problem. So let's first try to find solutions to A times U is equal to V. So A over here is going to be, for V, for U, I'm going to write x plus y. So I'm going to take A is 1, 2, 2, 4, x, y equals V. And the first equation is going to be 1 times x plus 2 times y is equal to the first element of V, which I'll just call V1. And here I'll say 2 times x plus 4 times y is equal to the second element of V, which I'll call V2. So let's try to solve this when V is equal to 1, when V1 is equal to 1 and V2 is equal to 3. And if you try to solve this, you'll see that you can't get a solution to this equation. So you solve for x in terms of y, it gives x is equal to 1 minus 2y. You substitute, everything cancels on the left-hand side, and you get 0 equals 1, which is never true, so there's no solution. You could have also come by this conclusion by noticing that this first row is a multiple of the second row. So if I multiply this equation by 2, I get 2x plus 4y is equal to 2 times v1. So that means for this equation to hold, 2 times v1 must be equal to v2. So it only holds in a very special case. So it doesn't hold for general v, it only holds when v1 is half the value of v2, so that 2 times v1. So this will only hold, for example, you could get a solution, you'd be able to get a solution of x in terms of y. You wouldn't be able to get a separate solution for both x and y, but it would be consistent if, for example, you had if v was equal to 1, 2. And we'll see that case later. But now what happens if v is 0 and 0? So then we try to solve this equation. And when you go through the analysis, it says that the first one is x plus 2y is equal to 0, which gives you y is equal to x upon 2 as a solution. And when you put y equals x upon 2, then there are an infinite number of solutions that will satisfy whenever y is equal to x upon 2. So that's what I said. Whenever this has a special relationship, or whenever y equals x upon 2, then you'll get an infinite number of solutions. So there's a theorem here about solving equations. And there's a graphical interpretation about when you get a solution, when you don't get solutions, when you get infinite number of solutions. So graphically, you can say, when you set up a matrix equation, the first equation defines a line in the plane, and the second equation also defines a line in the plane. If these two equations give you lines that are parallel, and you get lines that are parallel when the left-hand side here is a multiple of the left-hand side of the other equation, then it means these equations basically have the same slope, but they have different intercepts. Then you'll never get a solution. In general, if the two equations have different slope, then you'll get a unique solution. However, in some cases, when the equations actually coincide, then the two lines, all points on the two lines, satisfy the two equations.